Welcome back to Pre-Algebra with Miss Betsy. Today we are going to be completing our chapter regarding probability and statistics. Doesn't matter what text you're using, but if you're using the same one that I am, it should look like this. It is the first edition of Pre-Algebra for Christian Schools, published by Bob Jones University Press. We are in section 13.8 on page 468. Today we're going to be talking about dependent and independent events and the probability of those occurring. I've got a lame joke for you first. I wonder if you can tell me how many South Americans it takes to change a light bulb. Now there's a whole series of questions about how many whatevers it takes to change a light bulb, and the number of South Americans that it takes to change a light bulb is that it takes Brazilians of them. So let's go right ahead and get started with what we're talking about. I've got some aids right here. I have an old spinner and I have a quarter. Most of you probably played Twister growing up. You spin it, and depending on what color it is, you put your right foot on the red circle and your left foot on the blue circle and your left hand on another yellow circle, and you get all twisted up with everybody else. Now we're going to ignore the colors that we have here and just have the fact that we've got left foot, left hand, right foot, and right hand. So that divides this spinner here into 4 quadrants. So we have 4 possible choices of where the arrow is going to land when I spin the spinner. So what's the probability that it's actually going to land on right foot? Well, that probability is 1 out of 4, right? Because I have 4 choices. Only one of those is the left foot. So there is a 1 in 4 likelihood that when I spin this spinner one time, it'll land on right foot, or left hand, or right hand. And I spin it again, and I still have that same likelihood, for example, that I'll land on left hand. 1 favorable outcome out of 4 possible choices. Now, I know that you're all familiar with flipping a coin. Standard American quarter, heads on one side. See, there used to just be all the same many years ago, but we have the state quarters, so we have many different appearances to our quarters, but heads is one side, tails is the back. So if I flip it, what's the likelihood that this is going to be heads as it actually is? Well, that probability, or the likelihood, is 1 out of 2. Because one side of this coin is heads, the other side is not. So every time I flip this coin, there's a 1 in 2 probability that I'm going to get either heads. You know, if I want heads, it's 1 in 2. If I want tails, it's 1 in 2. Now, let's consider the fact that I have both of these things going on here. I've got my spinner and I've got my coin that I'm flipping. Let's say that I spin this spinner and I keep spinning it and I keep spinning it. Does it matter what result I get on this spinner? Does that have any effect at all as to whether I get heads or tails on this coin? No, does not have any effect whatsoever. So if we're going to spin the spinner right here, and we're going to flip a coin, those are what we call independent events. The fact that one occurs has nothing to do with the other. So what we're trying to figure out now is what's the probability of getting perhaps left foot on the spinner and heads on the coin. The way that you calculate that probability is by multiplying together the probabilities of each individual event occurring. So what's the likelihood of left foot? 1 out of 4. The likelihood of getting tails? 1 out of 2. You multiply those 2 probabilities together, and the likelihood that both of those will occur if you spin the spinner once and then you flip the coin once is 1 out of 8. So what if we wanted to know the probability of having a foot and heads? Well, with our spinner here, I have two favorable outcomes, don't I? I have right foot and I have left foot. So the probability of getting a foot is 2 out of 4, and the probability of getting tails is 1 out of 2. You multiply those two probabilities together, you can cancel common factors first. You have to make sure that this is reduced to lowest terms. And you have 1/4. So that's all you do if you want to determine the probability of two independent events occurring. And we actually have a formula that tells us how we deal with the probability of two independent events occurring. And it's written like this. It says the probability of A and B occurring, two separate events, not that we're going to draw letter A or letter B, but the probability of A occurring can be expressed by taking the probability of the first event and multiplying that by the probability of the second event, which is exactly what we did. Probability that we're going to have heads, probability that we're going to get a right foot. Let's stretch this out a whole bit. Let's say that we have a die that has 6 sides on it. What's the probability of getting a 2? Well, the probability of getting a 2 on a standard dice, there's 1, 2, and you have 6 possible choices. Now let's say that you have letter tiles that you've pulled from a Scrabble game, and you have one tile for each letter of the alphabet. And you want to know what's the probability of getting a vowel and getting a 1, or I'll just say that this was a 1, drawing that at the same time. Well, how many letters are there in the English alphabet? Well, there are 26 letters in the English alphabet. And how many vowels are there? We're just going to take our traditional vowels, A, E, I, O, and U. We're not going to say sometimes Y. We're going to say A, E, I, O, and U. 5 vowels. So in that bag of vowels that you're going to draw, in that bag of Scrabble tiles, you have 5 opportunities out of 26. So what's the probability that you're going to roll a 1 when you roll the die, and that you're going to draw a vowel? You can see it's not very likely, is it? It's going to be 5 times 120 plus 36. You have 5 chances, I think, out of 156. And those are what they call independent events, have nothing to do with one another. So now we want to see what we're talking about when we talk about dependent events. Let me just go ahead and rewrite this here. Probability of A and B, you just multiply their probabilities together. Well, what are we talking about when we talk about dependent events? This happens all the time if you have your name in a hat for a drawing for a prize or something. So let's say that we have this box here, and it has everyone's name in it. And I'm going to just put easy ones. Ann, Bob, Joe, Ted, and Sue. A bunch of 3-letter names here. Now, let's go ahead and draw what's the probability that we're going to get a girl's name on the first draw. Well, how many girls' names are in here? There's 2. Even though somebody had a poem or a song, a boy named Sue, we're going to say Sue's a girl. So you have 2 opportunities to draw a girl's name that first time, right? Well, what if we want to see what happens if we draw a girl's name first and then we want to draw a boy's name? What does that mean? What's the probability of drawing a boy's name? Well, it would be Bob, Ted, or Joe out of 5, right? No, it's not, because the first thing has already happened. We've already drawn a girl's name. So let's just say that we drew Anne's name. How many possible choices do we have now? That's right, we only have 4 possible choices. So if you have already drawn a girl's name, and now you want to see what's the probability of drawing the boy's name afterward, your number of total possible choices has decreased by 1. So your denominators are 4, and how many boys' names are there? 3. The way that you find the probability, oh, and these are dependent on one another, which I should explain. These are called dependent events because the likelihood of the second event occurring depends on what happened the first time. Okay? And just like you multiply the probabilities of independent events together, you do that same thing with dependent events, but your second ratio here is a little bit different, isn't it? You have one type of probability for the first time. We began with 5, and we said we want to draw a girl's name. So the likelihood this first time of drawing a girl's name is 2 out of 5 because we have 2 choices, divide by 5. But once we drew that girl's name, we only have 4 choices left. And we have 3 boys' names, and we multiply those 2 probabilities together. So you have 6 out of 20, reduced to lowest terms is 3/10, or 3 opportunities in 10 that you will first draw a girl's name from this box, and then draw a boy's name. Okay? Let's go ahead and see how they write this formula for dependent events. And they write this, they say, what is the probability of finding of A, then B occurring? First we draw this, and then after we have gotten this desired result, then the next thing has to happen. Those are 2 dependent events. So they say we're going to multiply their probabilities. Probability of A times the probability of getting that desired result given the fact that you've already had the first event occur. Looks really weird, but this is how it's expressed. Okay, let's go through some more examples and you'll see that this is really very straightforward. But this is read, the probability of dependent events occurring, the probability of first this, then this happening. Take the probability of the first event and you multiply that with the probability of the second event given the expectation that the first desired result has already happened. So let's go ahead and look at our example in the book. This is on page 469. And we're going to have just a little bit of a different example of drawing names. I really should have left the box back on, but I'm going to draw it again. We have Alan, Dick, and Carl are the boys' names in the box. And then we have Greg is another boy's name. Greg, Ellen, and Heather. And this is what our question is. And this is where we have to figure out what they're actually asking. This says select 2 names from the box. Select the second name without replacing the first name. Find the probability of a boy's name and then a girl's name. The probability of a boy's name, then a girl's name. What's the probability of finding a boy's name? We look at our original box here. We have 4 boys' names out of 6 possible choices. So it's going to be the probability of a boy's name multiplied by the probability of a boy's name, of a girl's name afterward. After you have already drawn a boy's name. Probability of a boy's name, 4 out of 6. Now, we have drawn that boy's name, so I'm going to just pick a boy's name at random. We're going to say we drew Greg's name. Now, we're not putting any more names back into the box. So what's the probability now that with this new set of conditions we're going to draw a girl's name? We have Ellen and Heather, only 2 girls' names that we have. Out of how many possible choices do we have? 5 possible choices. You multiply those 2 probabilities together, you have them reduced to lowest terms, and you have 4 out of 15. Because you have a common factor of 2 that you can reduce. And that's really all that is involved in doing these probabilities. Let me go ahead and take 2 or 3 right quickly from our homework problems. And you do not have to be able to write those formulas, but you have to understand how to get this. Okay, let's say that we have a spinner, and it says spin the spinner twice. Find each of the following probabilities. So this is a spinner, and we have 6 choices. And that is a horrible spinner, but we're going to say that it's even. And we have 6 possible choices of numbers that we're going to draw. 1, 2, 3, 4, 5, 6. What's the probability of finding a 6 and an even number? Two spins do this and this. Are these dependent or independent? They're totally independent because we're not changing. You know, the value that we get on the number we get on the first spin has nothing to do with the number on the second. So what's the probability of getting a 6? And what's the probability of getting an even number? And then we just multiply those 2 probabilities together. The probability of getting a 6 is 1 out of 6. The probability of getting an even number, 2, 4, 6, 3 out of 6. And then you multiply those 2 probabilities and you make sure that you have them expressed in lowest terms, so you can cancel common factors first or just reduce to lowest terms. The probability of those 2 events occurring is 1/12. Okay? These are independent events. Now let's do one with dependent events. And this one is from section C in our homeworks. You think, oh, that's going to be hard. Isn't hard at all. A, B, C, D, E, F, G, H. We have these 4-letter cards or tiles, and they're saying 2-letter squares at the right are drawn at random. The first draw is not replaced. Find each of the following probabilities. Probability of A, then D. What does that then tell us? It tells us that we're not going to go ahead and put that tile back. Probability of drawing an A, there's only one A over here, so that's 1/8, 1/8, times the probability of drawing a D, given the fact that we've already drawn an A. There's only one D, but now we have only 7 choices. So the probability of first drawing an A and then drawing a D is 1 out of 56. So go ahead and work on those. If you have any difficulty, send me an email, not an email, you know that, send me a text and I'll get right back with you. Otherwise, I'll see you on Friday.